In previous video, we made a language translation transformer from scratch in TensorFlow. And since we gone through the conceptual aspects in previous video, in this video we'll only focus on coding part because everything is pretty much the same. It's just this time we are not going to make it from scratch. Instead, by using high-level APIs like Keras NLP, we can do the same with much less effort. Keras NLP contains all sort of algorithms to build NLP solvers like transformer encoder and decoder, positional embedding, and so on. And these we will use in this video. And this is not like a Hugging Face transformer. You will still need to plug in the components. It's just not making those components from scratch. So without getting further ado, let's get started. Install the dependencies first. Remember, TQDM is optional in case if you wanted to see the progress of pre-processing or something. Import machine learning libraries, pandas to load the dataset, and clean text as its name sounds. TQDM is optional as you know. Define some hyperparameters, batch size according to the size of your model and your GPU memory, number of epochs, maximum sequence length. You can tune this sequence length according to your dataset and model size. We'll be making model with relatively small parameters because of resource constraints, so I choose a small sequence length. Define the vocab size for both input and target sequences, dimension of embeddings, dimension of encoded representation, and number of attention heads. Load the dataset. This is a conversational dataset contains actual conversation and summary of those conversation. You'll find the dataset on the GitHub link in the description. Now use clean text to perform the text cleaning by removing extra byte space or any URLs and emojis. Note that this time we'll keep the punctuation as it's somewhat necessary for this use case. And as you can see in this example, the person who said the sentence is actually represented by a colon. So this must needed for the model to understand who said what or to differentiate between the person and the sentence. Now filter out the sample which having less sequence length than what we defined in the max sequence length and store them in a list with a tuple of source and target. Once it's done, write a function to train Wordpiece tokenizer. But wait, what is this and why we are using Wordpiece? Let's understand how Wordpiece tokenizer and vocabulary works. Wordpiece tokenization works by first splitting the text into words and then splitting each word into subwords or characters depending on the frequency of that subword in the vocabulary. For example, the word unbelievable can be splitted into un plus double hashtag believe plus double hashtag able, where double hashtag indicates that the subword is not a standalone word. For example, here's a sentence. And at word level tokenization, it might mark technophile and coding as unknown, even though if the vocabulary contains similar words like technology or technical or code. But with the Wordpiece tokenizer, the words like this will break down into subwords like techno plus double hashtag file and code plus double hashtag ing. And in this way, Wordpiece tokenization can split unknown words into subwords that may be in the vocabulary and thus preserve some meaning of original word. It can also reduce the size of vocabulary and thus the memory and computation requirements for NLP models. Wordpiece tokenization can use a smaller vocabulary that covers most frequent words and thus result in a denser representation of text. If you want a dedicated video on this like how does it know which word to break into subword or how it's better from word level tokenization, let me know in the comments. Now let's complete the Wordpiece vocabulary. First, we'll create a data flow pipeline and then use compute Wordpiece vocabulary to start computing bag of vocabulary. Reserve some essential tokens which will represent padding, a known token, start and end token. Now get the vocabulary for both source input and target output sample, which is conversation as source and its summarization as target in this case. Once vocab is built, you can see some random vocabulary for both source and target. Now use Wordpiece tokenizer with already built vocabulary to compute Wordpiece tokenization for both conversation and summarization samples. Once it's done, let's check by tokenizing and detokenizing some random samples using both tokenizers. And as you can see, it done its job perfectly. Now that we have tokenization part ready, let's write a function to pre-process the data. Tokenize conversation and summarization first. Then use Keras NLP start and packer to add padding tokens for conversation sample like start and padding tokens to summarization samples. Return conversation sample for encoder's input and summarization sample as decoder's input. Now create a dataset pipeline. Get the source and target sample as list and put them into TensorFlow dataset with the defined batch size, map it to preprocess function and shuffle. You can try loading a sample just to test the pipeline. Now that we have dataset pipeline ready with the pre-processing steps, let's create model. Let's create encoder first. Make an input layer for encoder which will take tokens as input. Using token and position embedding with vocab size to get the embedding representation along with the positional encoding of the size of embedding dimension from the input tokens. Then use transformer encoder with Keras NLP to create encoder which will output encoded representation of shape of intermediate dimension and use defined number of attention head. And finally use Keras model to attach input layer with the encoder to complete the model. And that's how easy it is with Keras NLP. Last time we did all these from scratch. Now that encoder part is completed, let's make the decoder. Make an input layer which will get start token and encoded representation from encoder to get started. Use token and position embedding to get the embedding from the input token with masking. If you don't know why mask 0 is true, then you should watch the video on attention is all you need from the link in the description or from here. Use transformer decoder to create the decoder. Use dropout as regularization and finally connect the dense softmax layer to get the probability of predicted words. Now use Keras model with both the input from encoder and input for decoder to complete the decoder part. And hence, we have both encoder and decoder ready. We can use Keras model to connect the encoder and decoder to get a complete transformer. And as you can see, we have 6 million parameters, which is not big enough for a language model, and that's why I restricted the sequence size to 150 only. Next step is to compile the model and fit the dataset and train it for the defined epochs. Now the training has been started and speed will obviously depend on your GPU. By the way, I'll recommend you to use Google Colab for this. Once training is finished, then write a function for inference. Get the number of samples in input, then use input tokenizer to convert the text sequence to tokens. Now make a nested function which will predict the probability of next word given on the current input sequence. We'll discuss this prompt parameter in upcoming lines. And we'll use this function while simulating the autoregressive behavior of the decoder. Now for prompt, it's nothing but the array of size of maximum sequence length that's starting from start token followed by the padding tokens. This will initiate the decoder by being its first input with the start token. The name prompt is different in this video, else the procedure is same as the previous video. Now we'll use the greedy sampler which will take the token with a higher probability and stop when the model predicts the end token. After it gets done with the generation, return the detokenized sequence. Now get the source and target sample in two separate lists. And for 2 times, get a randomly selected sample as input sequence and pass it to decode sequence function we made above. Decode the output from tensor type to string and replace reserved token like pad, start or end tokens. Now print input sequence, predicted output and original output. And see, it almost captured the meaning and produced summarization output close to ground truth. But it's not perfect, like here it missed this whole part and here it missed the place. We can avoid this problem by reserving a token for these kind of representations. Some improvement in the model as well as large vocab size can solve these problems easily. The goal of this tutorial wasn't to make a perfect summarization model, but instead about working with each pieces of the model. Continuing this series will make a significantly large model than this in upcoming videos. Till then, stay tuned. Meanwhile, you should also watch this tutorial where I made a language translation model from scratch. And as always, thanks for your support and thanks for watching.